area.
Okay, that's fine.
Okay, so welcome everybody, and yes, we're pleased today to have as a speaker Luigi Alfonsi from Queen Mary of London, who's going to tell us about global double field theory and tensor hierarchy.
Okay, thank you very much for the invitation. As you said, I'm going to talk a little bit about global double field theory and tensor hierarchy, meaning only the tensor hierarchy of double field theory for now. So let's start. Let me see if this goes. Okay, so first thing, I will assume some slight familiarity with double field theory, but I'm not going to use any particularly complicated concepts. Today it will be fundamentally only about the geometry, so I will not be interested in particular things that I will not introduce after, and I mean notions about the basic notions about the tensor hierarchy of double field theory. So for now, it can be enough to think about double field theory as a T-duality covariant formulation of the supergravity limit of string theory. So the point of my research here is to try to understand how double field theory is globally in terms of geometry, because in the literature, of course, double field theory started as a theory mostly formulated on R2D or on a 2D dimensional torus, more specifically. So that's the very original formulation by Krystal and Zwieback. Then we also know in literature more complicated examples. For example, double field theory on group manifolds, such as the Drinfeld doubles. We also know double field theory of products of a D-dimensional non-doubled base manifold with a two-dimensional Lie group. So this is an example of whose global geometry is known quite well. We also know how to formulate double field theory on double torus bandos, which is the formulation proposed by Krystal. And if we look to the literature, we see that double torus bandos are not globally just to the dimensional torus, principal torus bandos, but they are actually affine bandos, because these local patches are passed by, in general, a subset of the affine patching conditions. So that this is something that must be taken note of. And so the question, by looking at all these concrete examples that can be found in literature, is how does a generally and not necessarily compactified, like for example a double torus band or this example where the fiber is taken to be a compact 2D-dimensional Lie group, how does a general example of double space look like in terms of global geometry? So in some sense, the question can be stated as how does a double manifold look like in general? So the question we may ask now is that can we, I said that double field theory can be formulated on a local chart like R2D. So can we glue these charts together, more or less like we do in Riemannian geometry, and make a manifold? So it can be done like this. You know, we have this double-dimensional chart, which is T-duality covariant. Can we somehow glue these things together and obtain a general notion of double manifold? There are reasons to believe that it is not so simple, as we can see in Riemannian geometry. The source of the problem is that this double manifold is supposed to geometrize the Kalb-Ramond field. This is because we have in some concrete examples, in particular the ones that revolve around the notion of double torus band, we know that the curvature, for example, in one dimension, that is the simple example, we know that the curvature of this extra circle that we add on space-time must be obtained by the fiber integration of the Kalb-Ramond field. So we immediately notice that there must be there is a geometric correspondence in this case between the Kalb-Ramond field and the extra coordinates. And we also know that ideally a double torus band should be just a particular example of this general notion of double manifold if we are able to precisely define it. So what is the problem of geometrizing the Kalb-Ramond field? So the problem is that the Kalb-Ramond field is locally given by a two-form, the B field. And these two forms are patched together on overlaps of patches of the base manifold in a more complicated way than just a gauge field, because they contain basically non-trivial information up to the threefold overlap of patches. So they are classified by cocycles, by check cocycles that are defined on threefold overlaps of patches. So if we know that, you know, these extra D coordinates must have some sort of relation with the Kalb-Ramond field, so they must be also in some sense glued together by taking into account that the Kalb-Ramond field is this geometric object here. So this, you know, like by working out the concrete cases, this can be a source of problem in defining a 2D dimensional general double manifold. So basically the motivation of this work is finding a solution for this, in some sense, is to define a double manifold which can somehow geometrize this geometric structure of the Kalb-Ramond field, which is a bundle gerbe. Now, another motivation is to make sense globally of tensor hierarchies. So now, what are exactly tensor hierarchies? So I mentioned the possibility that we make basically doubled only the fiber of our manifold, because in some sense is what we are more interested in, right? Because the duality is a duality that acts on the fiber, on the fibers of our space-time. So the notion of tensor hierarchy is basically a version of double field theory where it's only our fiber that is doubled. So at least our local charts should look like this decomposition here. So you can imagine that the problem could be, you know, how do I glue these things together and how does it look like? This will be the idea. So the field content of double field theory formulated as a tensor hierarchy in this case will be the following. So we will have G mu nu, that is a metric on the base manifold. Then we have this capital G, that is the generalized metric on the fibers. Then we have also a dilaton phi. But what we are more interested with is the actual field content of the tensor hierarchy. So we have a gauge field with 2D components, and we have a two-form field. So how do they work? So we have a chain complex between made up basically of functions on this double fiber and vectors on this double fiber. So these two objects can be connected by this differential here, which I define here, which is just the contraction of the tensor eta with the derivative on this double fiber. So this is what this derivative is on the fiber, and f here is any function is any function on this double fiber. Then we also
Luigi, can I ask a quick
Yes.
question? Could you maybe explain more where these fields come from? Do they come from like a G plus B on the total space? Or
well, in the original paper where they were introduced, which is this one by Ohm and Santrubin, they were basically derived by taking the generalized metric on the total manifold and making a Kaluza-Klein-like reduction. But
right,
also,
so that's where the A's come from, and
yeah.
So what's this phi then? Is this the component of the B field along the fiber or something like this?
Sorry?
What is this phi?
Phi. Oh, this is the dilaton because I will not mention it much during this talk, but this is, you know, when you have a double manifold with a generalized metric, that's not all the field content of double field theory actually, because there is also the T-duality invariant dilaton. So that's what phi is here. So yeah, you can obtain this field by reduction from a bigger generalized metric, but also it's not completely wrong to start from here, because in some sense, especially in exceptional field theory, often the exceptional field theories for the several dimensions D are defined in a fashion that is very similar to this one. So without going to the higher dimension and reduce, also because in exceptional theory that operation is much less obvious. So in some sense you could you could define double field theory in analogy with exceptional field theory in this form. But yeah, in the case of DFT can be reduced, can be derived this field content.
Okay, thank you.
And okay, so we have this differential here and this product here, and they are used to define the actual gauge structure of this tensor hierarchy. So these fields are a one form on the base manifold, which is valued in the vectors on the fiber. And then we have a B field that is two form on the base manifold and is valued in the scalars on the fiber. So if we want to make in the original paper by Ohm and Santrubin, when you derive the field strengths for these objects, you see that to make them truly T-duality covariant, you need to have a field strength of this form. So to make visually sense of this object, I put here, I define here a covariant derivative of this one form, like if it was a connection, because it effectively is a connection. And then I also called this term here Chern-Simons form of A in analogy. And these brackets here, the C bracket are I didn't write the definition here on this slide, but these are the brackets that encode the gauge algebra of double field theory. So they act on vectors, on double vectors, in particular on the fiber. So since this one form is valued in the vectors on this double fiber, we can act on the C brackets on them. So this is fundamentally what you get for the field strengths of tensor hierarchy. So this is the starting point. So this is known. This expression is known locally. Now, my question would be, so what is this total manifold in general? Because now I only talked about you know, a chart, just a vector space fundamentally. So my question would be, you know, this how does this tensor hierarchy look like globally, fundamentally? So we can ask, what is the underlying d plus n dimensional manifold, and what is the underlying global higher structure, because that's not completely obvious by this by this kind of definition, let's say, because we don't really know how globally they will look like, and that will be important to determine you know, the global structure of this kind of compactifications. If we want to classify them, if we want to make global observations about charges, about the moduli space as a global object. So these questions need to be posed. Okay, so okay, so in this slide, we'll give a super brief introduction of these geometric objects, the bundle gerbes. So they were defined originally by Murray and reformulated by Hitchin and Chatterjee in a more homological fashion. Let's start from a smooth manifold M, and we consider an open cover. If we want to define a circle bundle, we notice that this is basically encoded by default by a local U1 function on each overlap of patches, such that it satisfies this condition. So if you invert the order of the indices, you obtain the opposite. And then the important condition that makes it a cocycle is that on triple overlaps of patches, it needs to satisfy this equation here. Now, so this is a usual circle bundle. Now, how do we introduce bundle gerbes? An effective way is in total analogy with the circle bundle, because basically the bundle gerbe is said to be a categorification of the circle bundle, and probably this way of presenting it can intuitively suggest why. So we can define a bundle gerb in a very similar way to the circle bundle, but we need to define basically a circle bundle in each overlap of patches. And we have this relation here that is actually promoted to an isomorphism. It's not an identity anymore. And the opposite of a circle bundle here, for this object, I mean the circle bundle with the opposite first chain class. And we have on triple overlap of patches an isomorphism of this form. So we don't have, again, we don't have an equality, but we have an equivalence here. So in some sense, we could imagine a gauge transformation. So this generalization of the circle bundle is said bundle gerb. Then, yeah, effectively, we can think about it like as a principal bundle where the structural group U1 is replaced by a Lie infinity group, which is the Lie infinity group of U1 bundles. So I will just equivalently call a bundle gerb a BU1 bundle, so a higher principal bundle. Now, okay, so
sorry, question. This BU, I vaguely remember naming these classifying groups in classifying of vector bundles B of G, right? For a given G principal bundle. Is it the same construction here, or is just coincidental notation?
They are related. They are related. They are not exactly the same. It is also because usually this B here is written with a bold B to mean the stack. So so basically it is related because you can take this Lie infinity group and basically make a simple operation and obtain the classifying group that you mean. They are not exactly the same thing, because the classifying group, so if you consider the maps from M to BU1, the classifying group, you obtain basically topological classes of bundles. In this case, I literally mean this. You obtain by considering maps from M to BU1 seen as a stack. You really obtain basically the groupoid of these cocycles whose morphisms between them are the co-boundaries between these cocycles. So of course, if you take that object and you consider only the connected component of the groupoid, you obtain the classifying topological group that in some sense is can be seen like a sort of generalization. Is it preserves more information.
And for higher bundle gerbes, I'll need to replace it with even higher group derived from U1, or this is like enough for also higher bundle gerbes where I have more and more intersections coming into the game?
Oh, if you want to consider in some sense higher electromagnetic field, so not a 2-form or a 1-form, but like a 3-form, 5-form, etc. You will need to categorify more and more. So if you want to consider the geometric structure underlying a 3-form higher electromagnetic field, you will basically need the Lie infinity group bundle gerbes and not anymore of U1 bundles. So it would be increasingly more complicated, but in this case in a simple way. Then I will introduce later very quickly another kind of two bundle that is not this abelian bundle gerbe, but is something slightly more complicated. But
thank you.
It would be.
No, sorry, I didn't want to take that much time. Sorry.
Oh, no problem, no problem.
But thank you.
Okay, so now this is basically in this slide I put the the local data of the U1 bundle and of the bundle gerbe in comparison. So if if a circle bundle is given in differential data, basically on what we know in physics is the gauge field. So we have a local one form, which is the gauge field, and we have this this cocycle here, which is basically the transition functions of the bundle. We have that the gauge field is passed this way globally on a manifold, and it can in principle be a global one form on your manifold, but then you will automatically have that is topologically trivial. And we know that in physics, the most interesting situations, for example, if there are particles or charged particle, etc., are exactly when this is not trivial at all. Similarly, for the gauge bundle, we have a local one form, local two form that is our gauge higher gauge potential. Then on each overlap of patches, we have a one form that is a gauge transformation, and on each tripole overlap of patches, we will have a scalar that is the underlying check cocycle of the gerbe. So this is this in physical names, this will be basically gluing the Gall-Bramon field by using gauge transformations, and gluing the gauge transformation by using gauge of gauge transformations. So that's the intuitive picture about this. Now, so at this point, I will go more in detail with my research. So my question at this point was, is it possible to define a notion of atlas for a bundle gerbe? You know, because we can define quite simply a notion of atlas for a circle bundle, because that is very simply a manifold, so that's not complicated. And what happens if we define an atlas on a usual circle bundle? We have something very nice, a very nice application of that is Kaluza-Klein theory, which allows to unify a metric and a gauge field by lifting everything to the total space of the circle bundle. So the motivation of this question is basically, do we have anything similar? In the literature, there are some hints that we should have something similar, at least vaguely similar. So my question at this point was, how can we define an atlas for the bundle gerbe? So step one, a bundle gerbe is locally on any open set of the base manifold given by the open set times the structure group, like any principal bundle. In this case, the structure group is this Lie infinity group. So what I did then was to take this group that models locally the bundle gerbe and considering its Lie infinity algebra, which is its Lie algebra, its infinitesimal version. At this point, there is a well-defined notion by Fiorenza, Satie, and Scribe of atlas for a Lie infinity algebra. So in particular, an atlas for this Lie infinity algebra we are considering now is nothing but an ordinary Lie algebra A equipped with a homomorphism of Lie infinity algebras to our starting algebra, which is surjective in the lowest degree. So this will be the starting point of this of the look for an atlas for the bundle gerbe. So the idea here is that this Lie infinity algebra in some sense models locally the bundle gerbe. So if I can find an atlas for that algebra, then I can make Lie integrations and find an atlas for the bundle gerbe. So what happens now? To make the computations much easier, it is convenient to consider the Chevalley-Hillenberg algebras of all these algebras, which are basically their dual differential graded algebras. So there is a result that says that any Lie infinity algebra can be embedded by this kind of operations into the differential graded algebras. And computations for differential graded algebras are usually simpler. So in the case of this unknown Lie algebra that we want to determine, I will just write this one. So then in the case of the differential algebra, we are considering the underlying graded space is this one, and the differential is just always vanishing because it is an abelian algebra fundamentally. Even if there is a degree 0 part and a degree 1 part, it is fundamentally abelian. So now, instead of posing the question of what is A, what is phi, I will pose an equivalent but simpler question of what is this map here, because they are in one-to-one correspondence basically. So now, okay, so now there is a higher degree generator of this algebra here that I will call B. So for this map here, phi star to be an embedding of the G algebras, we need on the other side a 2-degree element omega in the dual algebra of our atlas, such that it satisfies these equations here. 0 because the differential of B is 0, since the differential in that the G algebras is always 0. So now the Lie algebra that satisfies this condition is immediately this one, where we have basically we still have RD, and instead of having this Lie2 algebra BU1, we have the dual vector space of RD. So how is that the case? Is because we have a simply defined omega that satisfies this very simple equations, which is omega given this way, where this E tilde and E are the generators in the dual, the G algebra, of these two components of our atlas. So if we define everything this way, we obtain that this omega is clearly closed, and we also have that the RD parts simply embed in this Lie algebra here. So the first conditions we put here, this this is an embedding. It is satisfied. Okay. So this Lie algebra here is the atlas for our starting Lie2 algebra. So now this atlas here can be immediately integrated to a map of Lie infinity groups. So effectively, we have obtained an atlas for our starting Lie infinity group that locally models the bundle gerbe. And we can notice that there is an analogy with, for example, RD plus 1 being an atlas for RD times U1, where our symplectic form plays a role which is very similar to the theta, where theta is the coordinate on the circle. So there is in some sense, this picture here gives a higher analogy of this kind of atlas. So we have an atlas for the Lie infinity group. Now the last step would be to glue this atlas together to obtain an atlas for the bundle gerbe. So we know that a bundle gerbe is locally given by this object here and patched together with morphisms and with higher morphisms. So if we compose everything together, we obtain an atlas for the bundle gerbe, which is locally made up of these 2D dimensional charts. Also, we used to have a symplectic form in the atlas of the 2 algebra. What happens for the bundle gerbe? Basically, that symplectic form is generalized to this object here, which plays a higher a role which is analog to the connection of a circle bundle on the total space of the bundle. It is very similar. So this object is globally well defined on the total space of the atlas because it is invariant under the gauge transformation of the gerbe. So if we apply the gauge transformations to all these objects, it will stay invaried. So this omega here can be thought as an higher analogous of the connection, for example, the theta plus A of a circle bundle. Now, so the conclusion of this thing is that we started from a bundle gerbe that codes the Gall-Bramon field, and we asked, is it possible to define an atlas for it? And the answer by defining the atlas like this seems yes. And these local charts are isomorphic to this vector space here, which is exactly what we would expect from double field theory in a locally, at least. Also, we obtain this 2 form here, which is usually called the fundamental 2 form in double field theory, and which is usually an important ingredient of the formulation. Then I've seen, of course, in the paper, I related this construction with other local formulation of double field theory in a more extended way. But what is the idea here? So so basically, the proposal is that this procedure can be summarized as the hypothesis that the global double space could be actually identified with the total space of the bundle gerbe, because in some sense, considering coordinates on a space could be considered the same of defining a working atlas on that space. So in this sense, if we define this atlas on the total space of the bundle gerbe, we have a 2D dimensional coordinates description which matches with the motivation of finding a geometrization of the Gall-Bramont field, and which gives rise to structure that are supposed to be found in double field theory. So what if exactly like we can unify a gauge field and a metric in Kaluza-Klein by lifting them on the total space of a principal bundle? What if it can be done exactly the same for a bundle gerbe? So what if double field theory is in some sense the bundle gerbe generalization of Kaluza-Klein? So to actually verify that to actually verify that this works, of course, we need to make a long list of internal checks. So first of all, we may ask, okay, this can be the underlying space. How do we define a double metric on it, a generalized metric? So it is possible to define globally defined objects on the atlas. To do so, we need fundamentally check that on the overlaps of these charts, they match after we define them locally on each chart. So, for example, by using the connection to form to define an object of this form that results to be globally defined on the total space of the atlas. So, okay. So in this part, I tried to construct a well-defined atlas for the bundle gerbe and see that it has the properties that you would expect in a local sense from the total space of double field theory. So now we need to slightly change argument, because I'm going to focus back on the tensor hierarchies. So tensor hierarchies will be actually an important test for this kind of proposition, because we don't know the global structure generally of tensor hierarchies. So can anything concrete be extracted this way? So now we need to change slightly topic and go back to a more abstract, higher geometric structure that will be very important for what it follows. So until now, I talked about only bundle gerbes, but there are actually other kinds of principal bundles with little groups. For instance, we can define a string bundle, which is given by cosychods that are valued in this string of G Lie infinity group, which is defined by a fibration of this form. So I will not go in the details of the theory about this, but in other words, this can be formulated as a bundle gerbe twisted by a principal G bundle, or even it can be pictured even in a more intuitive way by thinking about a principal G bundle and a bundle gerbe on that principal G bundle. So that's that can this structure can be lifted to that always. So we introduced these globally well-defined string bundles. So how they are bundles? How does how does their connection look like? It looks like this. So we have a local one form valued in a Lie algebra, the Lie algebra of the group G. Then we have a two form, local two form, not valued in the algebra. The curvature of this bundle can be written like this, and the Bianchi identities can be written like this, where D is the covariant derivative of the connection A. So this is a very short overview on the string bundles. So why this can be interesting now? Because we can immediately notice that at least here for the curvature, this is incredibly similar to the curvature of a tensor hierarchy, and that could be not incredibly surprising, since how the tensor hierarchy was defined. But this can be a very good way to try to give a global derivation of tensor hierarchies. So now I will introduce a very particular kind of string bundle, where the Lie group G.
Sorry, can I ask a question?
Yes.
On this slide, so the two form is now valued just in R. There's no like special values in tensor hierarchy, other bits, as before. Before you had one forms valued in R1, right, and two forms were valued in R2, yeah, which happens to be R in DFT. But is this perceived that way, or is it just whatever, just R here, and doesn't have any relation to the previous picture?
Okay, so in this case, the relation with the picture of the tensor hierarchies is not particularly strong yet. There is just a similarity. It is not. I will argue that they can be related in a stronger way. So yeah, for now these are just the bracket of the Lie algebra G, and they are valued. They basically take they are only forms on the base manifold, so they don't really depend on the fiber, while the tensor hierarchies are in principle allowed to depend also on the coordinate on the fiber. So I will now argue that the similarity can be made stronger. For now, definitely a general tensor hierarchy is definitely not just a string bundle. It is just related. It is true. It's probably true the opposite, though, that as I will see more. So now let's focus on a very particular example of that, which is an example where the generic Lie group G is replaced by a 2n dimensional torus. So in this case here, we have the classifying stack of 2n dimensional toruses, and here the one of the string of 2n dimensional torus band. So if we want to consider this structure, this will be just this will be a bundle gerbe twisted by this principal 2n torus band. Okay, so this is the definition of this particular string bundle. What does it give in terms of connection and curvature? So in terms of usable physics notion, we obtain this. So we have a connection that is one form but valued on R2n, and we have a two form. whose curvatures are given by this. And the Bianchi identities are the one that following. So they are a particularly simple case of the previous thing because there is no, we are dealing with an abelian group after all. There is no non-trivial Lie bracket. But the thing is that this field structure is exactly the global structure of a correspondence space in topological T-duality. So not any T-duality, of course, just specifically topological T-duality, where M is is one space-time until this is dual, and we consider the fiber product of them, thus the correspondence space of the topological T-duality. And that's not the end of the story, because we also have a higher field H, and its connection is B, which has these field equations. So the interesting thing here, even if we are incredibly far from the tensor hierarchy construction, the interesting thing here is that the field content on the base manifold of a topological T-duality is exactly a string bundle. Of course, if we want to consider only, if we don't consider the Ramon fields, etc. The field, the field structure of the topological T-duality is exactly given by a string of 2n-dimensional torus bundle. So, how can these go further? So let's, I tried to apply, or better, to generalize this notion to obtain some tool to study global tensor hierarchies. So we have, from the definition by Ferencz's transcriber, a precise notion of how we can dimensional reduce stacks. So I have basically, if my space-time is a torus bundle, I can consider a structure which can be a higher structure on this space-time and one but if I dimensionally reduce it on its base manifold, how does it look, that higher structure reduced on the base manifold? In general, you can imagine it would be super complicated, because if any differential data of that structure you want to reduce will depend also on the coordinates, on the fibers, so it can be very complicated. But there are some simpler cases. For example, topological T-duality fits in this kind of examples. And if we consider a bundle gerbe on our space-time, and if we impose the condition that this bundle gerbe is equivariant under the principal action of the torus bundle, so in some more intuitive way, none of the differential data of the bundle gerbe depends on the coordinates of the fiber, which is more intuitive even in more physical terms. If we impose this condition, then this is exactly a string Tn times Tn bundle on the base manifold, which we already saw that this is the geometric picture of a topological T-duality. So is that surprising at this point? If we know that the string bundle here is defined as a bundle gerbe that is twisted by a principal bundle, then in that case, it's not incredibly surprising, right? Because a twisted bundle can be visualized as a bundle over a bundle, right? So it's not really the most surprising thing here, but it fits with the idea that generally we may try to define the global tensor hierarchy, or at least a class of global tensor hierarchies, as a general dimensional reduction of a gerbe. Because we, in the first part of the talk, we argued that the geometric picture of the double space may be globally seen as a bundle gerbe. So the fact that by reducing the differential data of the bundle gerbe to the base manifold recovers in a global form the fields that we want from double field theory, such as the topological T-duality structure. That's quite consistent, at least. So, okay. So a question that we may ask is that, you know, we have our bundle gerbe, but what happens if we try slightly more general reductions, at least? And the next and probably very last part will be about T-folds. So check very briefly how the global geometric structure of a T-fold can be defined in this way, starting from a gerbe and then reduce it. In some sense, you could see this kind of operation as an attempt to make globally define some operations that were done in double field theory, even since the very beginning, but in a local, mostly in a local fashion, at least. So, and this is also very interesting for a second reason, because we see that by reducing a bundle gerbe, we obtained a doubled dimensional fiber. It is something that happens very naturally. It's not something that we need to postulate. It's not something that we need to insert in the theory that the fiber is artificially doubled. So what happens with more general things? So when the duality is not topological, but the other side of the duality is not as nice as a smooth manifold, what happens in that case? In that case, it's more complicated to work out exactly what happens, but we can start still from a torus bundle because it's the most simple example. We can consider the connection of this torus bundle. And now we can ask that the curvature of the gerbe is invariant under the action of the principal bundle. This is basically the T-duality, is the T-duality condition. Like if we don't need to ask that the two-form Kalb-Ramond field is invariant under the action. The minimal condition is just that the curvature is to actually have T-duality. So let's impose this condition on the gerbe. Now, what one can do is really take the differential data of the gerbe and expand them in the connection, which is globally defined on the global space of the torus bundle. So you can expand everything on every patch. And once you do that, you can make some field redefinition. So starting from the last, you can identify these two-form components that you obtained by expanding the original two-form with this script B. Then you can put together the original gauge field with the one-form components that you get from the Kalb-Ramond field and make this field here. Then you can take the curvature part, so H3, the three-form component of the original H, and you call it like this. Then you can take the two-form curvature of the torus bundle together with the two-form that you obtain from the curvature of the Kalb-Ramond field. But you make also a bit shift to this thing, and you can define this as by this script f. If you make this redefinitions, these fields satisfy exactly this equation here upon strong constraint. So we also see this term here appear, the one that depends on the coordinate of the fiber. And so we are basically reducing to a very simple case of, an extremely simple case of tensor hierarchy. But in this case, this is globally well defined because it's defined by considering the gerbe and dimensionally reduce it on the base manifold. So what happens? I should probably go very, very fast here. So we can pack together the coordinates of the original fiber and the new tilde1. We can construct a one-form connection for all these local double torus bundles. And now we want to see how the gerbe picture implies that these objects are patched together. So by doing some computations that can be actually, this part can be, is already computed in the literature. So you can find a cocycle of this form and construct its exponential, which will be basically a local ONNN transformation on each overlaps of patches. And you will see, and I will describe this very briefly, that these local connections of the tensor hierarchy are patched by using these ONN monodromies. Same story for the curvatures. If we want to introduce also if we want to put inside the generalized metric, we will see that this is patched also by using this cocycle here. And the one form that is actually globally defined is not our tensor hierarchy connection, but it's B-twist. By applying this B shift here on each patch, so what we obtain at the end of this operation is a global one form. So basically, by starting from the bundle gerbe, by reducing it, by imposing minimal conditions of T-duality, what you get is this picture of how the fields of the tensor hierarchy, including the double metric, are passed together. And this is not also an interesting thing is that it is not globally it is not globally a higher gauge structure, because it is actually passed on each overlap of patches by monodromies. So the general global picture is a little bit very slightly more complicated than just a higher gauge structure. And interestingly, non-geometry can be connected to a topological properties of this manifold, because we basically have non-geometry T-dual when the extra coordinates we introduce. So this extra torus fiber that we introduce is topologically twisted in a principal bundle sense over the underlying torus bundle. So, okay, and I think my time is definitely over, so I will skip the very last slide, and I will probably leave you this. So basically, by doing this, by performing this dimensional reduction of the bundle gerbe, we have two pictures, because I made the field redefinition of the same objects. These two pictures are related by B shifts on each patch. And on one side, we have the tensor hierarchy descriptions where we have this local 2n-dimensional torus bundle patched by monodromies. And in the other picture, we have the generalized correspondence space. So what we usually find in the literature when we want to find about T-duality, when the T-dual is not well defined, is usually introduced the generalized correspondence space, which is a more general version of the correspondence space. So these two pictures are related, and they both come from the dimensional reduction of the gerbes, just by making some little field redefinition, which amounts to a bit shift on each patch. So now this replies to the question: how does a tensor hierarchy, so simple tensor hierarchy of this form, patch like globally? It does patch by involving also ODD monodromies, and that is something that follows from the reduction. Then, of course, the natural question would be, what happens if I don't consider just torus bundles that are easier but G bundles? And there are things that can happen, because we can obtain. Is quite complicated to work out, but one can obtain by reducing a bundle gerbe on a non-abelian principal bundle, you can get some more general structures that are particular cases of tensor hierarchies, but globally defined, and they involve they involve the behaviors that we do expect from non-abelian T-folds, or at least from what we know until now from non-abelian T-fold. But I will go to the end, because I think that my time is really at the end. So basically, we saw how the bundle gerbe, both reduced and not reduced, seems to have geometric behavior that we would expect from a candidate of global definition of double field theory. And this kind of formulation can ideally be generalized to many other kinds of principal infinity bundles. So try to use even higher structure to investigate exceptional field theory. So consider, instead of just a gerbe, consider a non-abelian generalization of that gerbe to investigate global heterotic double field theory, and etc. So that's ideally, if it is possible to show this work generally for any kind of example, it would be a sort of higher generalization of Kaluza-Klein in some sense, but not constrained only to principal bundles, but which can work with any Lie infinity structure group. Of course, they are not all interesting for physics. So thank you very much. I think this is the end. I used a lot of your time, and thank you.
Thank you for your nice talk.
Thank you.
Are there questions?
I guess this second last slide that you had just before the outlook with the non-abelian T-fold, I guess the same thing follows almost immediately for any Poisson-Lie T-dual stuff, right? Because this global one form, this like twist that you have here is like where you twist by, this is the ODD transformation, which kind of implements your non-abelian T-duality. But I mean, this is also you can write down a similar expression for Poisson-Lie T-duality as well. So I imagine that if you just do the same thing and replace it by the same ODD matrix, then
yeah, I think I mean that's what I would expect. That's what I expect, at least. Of course, the complicated part is more to I mean, the computationally complicated part is to derive it by making a reduction of the cocycles that define the gerb in the non-abelian.
Right. So this would be the answer, which you would expect.
That would be, like, if I find another answer, that would be a problem. But,
Cool.
And then the interesting thing is that the fact it was very puzzling in non-abelian T-duality at the beginning. It actually still is that you have a big shift that depends also on the T-dual coordinates. Even if you didn't even define the T-dual coordinates, they already are in there. You say, well, how is that possible?
And it's the same in Poisson-Lie generically as well.
Because it does follow. I mean, it is probably more a property of the the classical Drinfeld double that this happens. But the interesting thing is that you can derive that by reducing the bundle gerb. You would it's like for the abelian case, you wouldn't expect in principle that you start from a gerb and you end up with the double fiber embedding in a higher structure, but you still have an underlying double fiber. And it's very similar. It's very similar for a doubled Lie group in some sense. It does the job. It would be interesting. It is my interest to try to make it in a more to connect these not just in these bundle terms, but to connect it more directly to the algebra, to the Lie algebra behind that. So if I can linearize many of these things, can I make a connection between the Lie algebra of the Drinfeld double with the two algebra of a linearized bundle gerb on SU2, for example? That was interesting to me.
Yeah, nice.
Luigi, can I ask you, is there any kind of relation to the reduction of Courant algebraids?
It must. I think. Is this that? That's a good question, because it's not really so different, because as far for what I understand, Courant algebroids, they are. I mean, at least a class of Courant algebroids can be interpreted as underlying vector bundles as twisted by a gerb. So if, in some sense, when one reduces the differential data of the Courant algebroid belonging to this class, in some sense, is doing an operation which is very, very analog. It's just my is that I think that in some sense. I don't know exactly how it works for very general Courant algebroids, to be honest, because I always thought it in the case where, okay, I have a Courant algebroid which is basically a generalized tangent bundle twisted by a gerb, then I reduce the underlying gerb, and so I didn't think about a very, very general case, but they must be, they are definitely closely related.
Okay, thank you.
I'm a bit curious about how really the dimensional reduction in the case of stack work. Is it is there any short explanation, like it's a weak equivalence of spaces or something like that, or so more?
The general case is very. The general case is not particularly simple, and I guess I would have to see an example to work it out, because, for example, yeah, I mean, even if you consider a simple stack like the moduli stack of circle bundles, that's quite complicated to reduce. I mean, I would try. I did it manually in some sense in my papers. Like I literally took the differential data, the cocycles, and I reduced them to see what you were obtaining. I guess that there are probably some simpler ways in other cases. Yeah, of course there is nothing as simple as this one, because when you define a twisted bundle, you already know that can be in some sense interpreted as a bundle over a bundle. So that's very immediate. In the general case, I think in the general case it's too general. I don't know. I'm probably not the best person to ask.
I just wanted to know if there is some leading idea which give you a clue how to do it in general setting.
Yeah, you should. I think you should consider basically you need to consider basically the space of maps. For example, if you are reducing over a group G, I guess that the abstract definition would be to consider the group of maps from the group to your stack. So, for example, if you want to reduce over a circle bundle, you can consider the loop space of that stack.
Okay.
In some sense, that is, you know, it's yeah, it would be basically the loop space where you slash the action of the circle. So for other kinds of fibers, it's basically the generalization of that. So you have basically this in some senses the generalization of that. So so if you want, even if you want to reduce if you want to reduce if you want to reduce any stack on a circle band, you need to consider something that is closely related to the loop space of that stack. And then more generally, I don't know.
Okay, so it's a kind of quotienting some loop spaces.
It is basically a very general notion of transgression, I would say. It's basically a very general notion of transgression.
Okay.
Yeah.
Mm-hmm. Yes, thank you.
Thank you.
Maybe I have a naive question. Can you make a comment also about para-Hermitian geometry? Like, so why would you defend your formulation over para-Hermitian geometry?
Yeah, right. I didn't say anything here actually to make it simple. but it is true that so this actually makes stronger the connection with what we know until now of double field theory, because so here I was trying to find an atlas for this little algebra, and the objects that you find is this vector space here equipped with this symplectic form here. So if you put together also the fact that this splitting here of A into D-dimensional vector space, one the dual of the other, is canonical because it's given by the embedding of the chart of proper space-time inside. So if you consider this is canonical, basically this splitting is equivalent to giving a permission structure on A, because sorry, not a permission structure, but a complex structure on A, because that is equivalent to specifying a splitting of this form. So if you put everything together, this atlas is made up of this vector space here, a symplectic form omega, and a paracomplex structure, which is very simple in this case, J. So basically, this vector space here is a paracalar vector space, and I think it's probably I mean, it could be not so interesting, but it looked interesting to me that if you take this linearized version of the gerbe and you try to find an atlas, you end up with a paracalar vector space. It seems to create a very intimate correspondence between para-Hermitian geometry and higher geometry. Then, of course, in this case, it's a very simple paracalar space, but by trying to gluing all these atlases together, you find an omega which is not anymore symplectic, and a paracomplex structure that is not anymore so simple, but is still something analog, because it's the paracomplex structure that you can introduce here is still implied from the splitting between the starting space-time and its dual coordinates in some sense, because since I started from a bundle gerbe on a very well-defined space-time, that splitting, it's still canonical in some sense. Then I also saw in my last paper about that if you this thing can be made stronger, because if you consider the atlas of a bundle gerbe and you've considered the atlas of the T-dual bundle gerbe, so in a topological T-duality, you see that these two atlases are basically isometric in the para-Hermitian sense. So they can be so basically, if you take the first one and you perform an isometric transformation, then you end up with the other one. So in some sense, the underlying manifold is the same. What changes is the polarization of the paracomplex structure. So I think that this seems to say that in some sense, para-Hermitian geometry could be. I don't know if it is more general than that. It could be more general than that, but at least it can be used also to describe, in some sense, this kind of atlas for bundle gerbes, which is an interesting connections by bundle gerbes and para-Hermitian geometry, which are it is not obvious that they have this kind of relation.
Okay. I see. Thank you.
Thanks.
Are there more questions?
Maybe I return to Andreas' question. So if you write BU1, for example, so you don't really mean like the topological group, the infinite dimensional. You mean like the crossed module, right?
Yeah.
To group unit, right?
Yeah. Actually, my later code, I wrote this not with this font, so it was more obvious. I mean, it was more visually that I didn't mean the same thing, but they are they are strictly related. But I do mean the
if you take, yes. So one way, of course, is to take the nerve of the two group and geometric realization, and then you get the topological.
Yeah, I do mean I mean the moduli stack, let's say, not the moduli.
Yeah.
I probably should have explained it, because I really didn't say anything about it. It is basically, I mean, for the purpose of this slide here, can be thought as the group stack of circle bundles, meaning that we basically have you know, the objects of this groupoid would be the circle bundles. Their morphisms would be the gauge transformations, and then you can define a tensor product that satisfies the group defining equations up to an equivalence. So there's also a picture that can be made of it, but in any case, yeah, I mean the object that can be written as a crossed module, right? That's
yes, okay.
Well, okay, then I think we can conclude the seminar, and thank Luigi again for your nice talk.
Thanks to you.
Thank you.
Thanks to you.
And have a happy Easter break.
Happy
you
Easter
all.
to all of you.
Yeah,
thanks.
okay.
So, I don't know, maybe, wait, I can stop very quickly.